Not excited about the rain? I'm just hoping if it's going to rain, it rains soon. Because I don't want it to be raining when I go home tonight. Like that does not give me joy to drive through 2 inches of water for 40 miles. It's just bad. Do you guys have any questions about Mission 10? Problem 158? Yeah, I can do that. Now, I might get stuck on this. About every other time, 50% of the time I try to do this problem, I get stuck. Just so you know. So we know that going into it. It's not hard, but I've just got a mental block on this particular problem. But let's look at it together. Problem 158. So there are sort of two camps in calculus on how it's taught. There's a lot of instructors who do not teach exponentials and logarithms until the very end. And before that, they'll just focus on polynomials, sine, cosine, rational functions, algebraic functions, but no logarithms, no exponentials. And the reason for that is they would say something along the lines of, there's no good definition for the exponential, there's no good definition for the logarithm before that point. And okay, I mean, if you really take a critical look at our definition of exponential, you'll find out that there's a kind of slightly non-intuitive leap that I made to define the number e implicitly through a limit, which I guess technically I never proved existed or something, but there's a fair number of things in calculus we don't actually prove, all right? But anyway, problem 158 shows you how the other world, the other camp of people think about the logarithm. And so what this problem does is it discusses an alternative definition of the logarithm. And come on, I do not need an extended warranty on my car. Shut up. You know, you'd think hitting the red button would make it hang up, but apparently not. All right. So the alternative definition of the logarithm is this, and we're just going to call it f of x because we don't want to inadvertently use the logarithm or its properties in this problem because we're trying to show that this function behaves. I mean, the point is, after the dust settles, we want to be able to say, aha, f of x is really log of x, all right? So want to see f of x same as natural log of x. That's like the big picture desire of this problem, okay? Now, it's very tempting for me to just do part A, you know, because A I can definitely do. But maybe, you want me to do B? All right, I'll try to do B. That was your target question, all right. I would just point out that A is f of 1 is 0. Can you tell me why A is true? What's the integral? Maybe we didn't actually talk about this, but what would the integral from a number to an... Actually, this is probably a deficiency of my current definition in the notes. But, I mean, in fact, I should probably mention this definition. The integral from A to A of, you know, let's say f of t dt is 0, okay? If your integration region is just 1 point, then there's no area. Yeah, I mean, now actually in differential equations, we study functions which are called, well, I say quote unquote functions. There's something called the direct delta function in differential equations where you have integration over just one point, which gives you a finite number. But that function's actually infinite at that point. So that's past calculus, all right? I'm just saying that there is a context in which integrals over one point can give you a number, but this is not it. Okay, so the question is f of xp equals p times f of x. That's what why is that true? Explain this. All right. So let's write it down. F of xp, x to the power p, is equal to the integral from 1 to x to the power p, right, dt over t. Let's see here. Now, in the footnote, I mentioned that you can use the power rule and properties of the integral. And for part B, I say for part B, so this is like just a general idea in calculus. If you kind of look at something, you're asked to prove something, you just don't know what to do, right? Oftentimes, a successful strategy is to say, invent a function, in this case, h of x, where that function is 0, that function being identically 0 gives you the truth that you're looking for. So like this identity that I'm trying to prove, f of xp equals pf of x, that's the same as this function h being equal to 0, right? So I've traded an equation for a sort of more concrete task of showing that this function is identically 0, right? Show this is 0. So what we're trying to do is show h is constant, right? So how can you show a function's constant? Well, you show its derivative is everywhere 0. All right? So what we need to do then is calculate h prime of x. So that's d dx of f of x to the p minus p times, well, df dx, right? But let me write out more fully what that is. That's d dx of the integral from 1 to x to the power p dt over t minus p times the derivative of the integral from 1 to x dt over t. Now, fundamental theorem of calculus part 1 tells me what the second derivative is. What does that work out to? What is this equal to? What does FTC1 say? FTC1 said, remember? It said that the derivative with respect to x of the integral, let's say from a to x of, let's say, g of t dt equals to just g of x again. That's what the fundamental theorem of calculus part 1 says. It says the derivative of the area function is the function being, function for which you're finding the area under it. So this, here, g of t is 1 over t. So this is just 1 over x. In contrast, here we have x to the power p, right? So there we need to use the chain rule, or FTC3 as I call it, and this gives us 1 over x to the power p ddx of x to the p by what I call FTC3. and that's minus p over x. Still that. Of course, that's why I put that footnote there. For part B, it's useful. Well, I also, in the footnote, I said you need to know the power rule, which is p times x to the p minus 1. And how does this simplify? Well, that gives you x to the minus 1, right? So you got p over x minus p over x. So indeed, h prime of x is 0. So that shows us that h of x is constant, since h prime of x is 0 for all x, right? Now we want to show that that constant is 0. So what number should we plug in so that we can actually calculate what h of x is for all x? What number stands out to you as a nice number to plug into this function? 1, right. H of 1 is f of 1 minus p times f of 1, right? But from part A, we already know that this is 0, and this is 0, so this is equal to 0, which is, of course, also equal to that constant. Therefore, h of x is 0, which is to say that f of x to the p is p times f of x, right? That's really good news if you're an advocate of this viewpoint, because that just, you have now proved the power rule for the logarithm. See, because this is more familiar if I write it like this, right? Natural log of x to the p is equal to p times the natural log of x. This calculus shows that if you define the natural log in terms of this integral, if you give this integral definition for the natural log, you get the power property for the log. Part A shows you you get the natural log of 1 is 0. And part C is the other property of logs, right? Log of the product is the sum of the logs. So there you go. Let's see here. Another thing I should talk about here, before I forget, is even and odd functions, all right? Let's talk about even and odd functions, because there's a homework problem or two about that, and I haven't systematically discussed those things yet. And in other words, what can we say about the integral of an even function or an odd function over an interval which is symmetric about the origin? See, there's some very, very nice things that happen here. Now, I can give you a geometric proof, or I can give you a U substitution proof. All right? I will give the geometric proof and the U substitution proof. All right, so first of all, what's an even function? F of minus x equals to what? Well, let's say for all x in the domain of f makes f even. By definition, even function, right? In contrast, if we have f of minus x equal to minus f of x, then that's a what? odd function, right? So here's a observation, or you could call it a theorem, whatever you want. I'm going to call it an observation this time. Number one, the integral from minus a to a of f of x dx is equal to 0 if f is odd function. To the integral from minus a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx if f is even. And here I'm saying for f with minus a to a subset of the domain of f. Actually, I only have enough room on this particular chalkboard to give geometric proofs. So let me just give you the kind of geometric proof here. What is the graph? So let's deal with the odd case first, right? So what does the graph of an odd function look like? It's the same shape, right? But flipped over. So the reason this is true, of course, is because whatever area is above on the one side is below on the other. You know? So they're equal because of the symmetry, because the function's odd. So this area and this area are equal and opposite. This one's, plus. This one's minus. So the net signed area is 0. On the other hand, if it's even, right? I mean, it doesn't have to be, it could be, by the same token here, this area and this area are equal. Same shape, just flipped over the y-axis. And consequently, you can just double the area from 0 to a. And I say area, but I should say signed area. So if you know a function is even or odd, and you know about the integral over part of the, you can extrapolate from like positive to negative and vice versa. And let's see here. So let me give you the U substitution proof. Now, should I do it for even or for odd? Actually, let me just give you the argument for arbitrary function. If we're integrating from minus a to a of f of x dx, right? I want to change that integral to an integral of f of minus x. All right? So what I do is I let u equal to minus x. That will make x equal to minus u, right? And it also makes, du is minus dx, right? And what else can we say? X equals to a, u equals to minus a, right? X equals to minus a gives me u equals to a, right? This is the substitution. And so this substitution of u equals to minus x, it flips the bounds, right? It flips the bounds over because we have to change the substitute. We have to substitute the bounds. See, this goes from this goes a, this goes to minus a, and this is f of minus u. And oh, I think I'm about to do something pretty stupid. Minus du, all right, right? And so I have minus the integral from a to minus a of f of minus u du. And remember the rule, one of our definitions for the definite integral was that if we flip the bounds, we get a minus. So this is the integral from minus a to a of f of minus u du. All right? But in this case, we don't have to write u. We could just as well write x at this point. We could say, okay, well, this is really just the same as the integral from minus a to a of f of minus x dx. So going from here to here is called swapping the quote-unquote dummy variable of integration. So you notice that, I mean, this is something we don't talk too much about in Calculus 1, but it's worth mentioning. The whole process of doing the definite integral, it's a number, right? So like the x you use in the formula, this thing, right? Integral. This is basically the idea. Integral of f of x dx, by the way, is equal to the integral from a to b of f of t dt. By the way, that's equal to the integral from a to b of f of Pac-Man d Pac-Man. It doesn't matter what you call the variable of integration. It's the same number because it's just a notation for the same limiting process of an infinite sum. So we have this freedom of changing the letter of a dummy variable of integration. So, all right. This is both true and useless. Let me show you where its truth is helpful. We have this is equal to that, right? So suppose f is odd. Yeah, well, I said it is given for point 1, but for point 2, f would be even, you know? I didn't assume either so far. I just had a function. All I've assumed for the function is that its domain includes minus a to a. If f is odd, then f of minus x is what? Minus f of x, right? So the red underlined equation gives us what? It gives us the integral from minus a to a of f of x dx equals minus the integral from minus a to a of f of x dx. What's that tell you? Twice the integral from minus a to a of f of x dx equals to 0, right? Therefore, the integral from minus a to a is 0. Now, why did I say this is also useless? Well, how about the case f is even? What does the red underlined equation tell you? I mean, if f of x is even, then f of minus x is equal to f of x. So what the red underlined equation tells you is that the integral from minus a to a of f of x dx is equal to, well, the integral from minus a to a of f of x dx, which is true, but is not especially helpful, right? Like this is not how to prove number 2. To prove number 2, what you need to do is to basically do this same kind of argument, but instead starting with the integral from, say, minus a to 0 of f of x dx, right? That's the integral from 0 to a of f of minus u times minus du. Excuse me, 0 to minus 0 to a. Making that same substitution. And then you flip the bounds, and that flipping the bounds and this minus comes together to give you integral from 0 to a of f of minus u du, which is equal to the integral of f of u du from 0 to a for f even, which then gives you, the integral from 0 to a of f of x dx, switching dummies. So that tells you that this is equal to that, which is all we need to get that the integral from minus a to a is twice the integral from 0 to a, right? Because this we can break up into 2 pieces, Oh, why did I do that? See, because this one here, we can take that and write that as integral from minus a to 0 of f of x dx plus the integral from 0 to a of f of x dx, right? By one of our basic properties. And then this is the same as that, right? By that argument over there. Therefore, it's just twice the integral from 0 to a. Okay, anyway, I think I've spent more than enough time on that. So now that I've told you these things, can you see how to do like problem 156? Dx equals 7? Oh, the integral. Oh, okay. Right. Yeah. If I ever write dx equals to 7, you should kick me out. You should be like, write the dean a letter, say, this math professor has written dx equal to 7. You need to fire him. Kick him out in the street. No, I'm just kidding. Don't do that. All right, so just to give you a sample, let me give you an example of how these properties, play out. Problem 156 is the one good example. I'll let you guys work on that one. I think you should think through it for yourself. You have everything you need to do that now. You just need to use these properties. But another example would be something like the integral from, say, minus 10 to 10 of the hyperbolic tangent of x plus x times the cosine of x dx. You see something like this, right? You should be like, well, maybe I can integrate hyperbolic tangent. In fact, we could do that one. We'll do that one next. But here, let me make it so we make it so we really don't want to do it. 13th power there. Now it's unpleasant. So you see something and you're like, I don't know if I can really integrate that. You'll actually learn how to integrate x cosine x in calculus 2. That's an integration by parts problem. But anyway, what I would point out to you is if we call this thing f of x, right? What's f of minus x? It's tanh of minus x raised to the 13th power plus minus x times the cosine of minus x, right? But the thing is, tanh is what? Remember, tanh is sinh over cosh. Now, sinh and cosh are respectively odd and even, right? So what happens when you put minus x into tanh? Well, that gives you back my point is that the hyperbolic tangent is an odd function. All right, hyperbolic tangent is an odd function. And so this is just minus hyperbolic tangent of x raised to the 13th power, right? What was cosine's even, right? So that's minus x cosine of x. Since cosine's even. We're not differentiating, we're just evaluating at minus x. What I'm trying to show you right now is, in fact, the function we're integrating, it's an odd function. We're almost there. So minus 1 to the 13th power is minus 1, right? So you look at this, you got, oh, in fact, this is minus, parentheses, tangent 13th power of x plus x cosine x, right? In other words, that's minus f of x. So f is odd. And so we have the integral of an odd function over a symmetric interval of the origin. Therefore, this integral is we just proved for any odd function, if we integrate from minus a to a, the integral is 0. So once you know this, you go, aha, game over, 0. So. All right, well, now that I have that out of my system, I think I'm going to spend the rest of class today focused on integrals of trig functions, okay? Unless you guys have another question about homework. So we have a lab Friday, and I'll collect mission 10 Friday. I should have the solution to mission 9 up sometime soon. Sorry I don't already. My bad. I keep meaning to do it, and then I get carried away with pouring concrete on Tuesday or Thursday, and then I just fall asleep in my chair after that. It's just like, I don't know. All right, so let me finish. Well, actually, can I erase this? You guys got it? What's that? Oh, okay. I'll get out of the way. All right. Let's see here. So last time we found a nice identity for how to integrate like products of sine and cosine. Can you guys remember? Tell me what it was. We found that, what was it? Was it cosine? I can't remember. Cosine of ax times the sine of bx. What was it equal to? 1/2. sine of something. I guess it was sine of a plus b x, and then plus 1/2 sine of, I think it was b minus a x. Yeah, that works. Okay, so let's see, what other patterns might you be interested in? It would be nice to know about. How about, what if we have cosine ax times cosine bx, right? It might be nice to know the formula for that as well, right? So let's work that out. I'll use my trick, my secret trig. So that's 1/2 e to the iax minus, or rather plus e to the minus iax, and then 1/2 e to the ibx plus e to the minus ibx. And then we just do algebra, right? So we got 1/4 e to the I a plus b, and then, so that's this times that. This one times that one gives me plus e to the minus I times a plus b x, and then plus a 4th e to the I, well, we can do b minus a, let's say, x plus e to the minus I b minus a x. So just to tell you where this came from, this one has come from the product of this guy and this one. So notice that minus minus gives me a plus, and the other two, it's the product of e to the minus iax and e to the ibx. But the larger point here, of course, is that it goes back to the fundamental formulas, which I told you last time. Cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta is 1/2I e to the I theta minus e to the minus I theta. So like with those, I boxed them in last time, boxed formulas in mind, you can look at this and go, aha, what I'm really looking at here is 1/2 cosine of a plus b x plus 1/2 cosine of b minus a x. And there you go. Product of two cosines gives you a sum of cosines. Of course, there's one left to do, right? Which would be sine with sine. How's that going to work out? Well, let me be a little bit lazy. Let me call this thing t, and let me call this thing theta for just a second here. So notice that we have cosine of t times the sine of theta is equal to what? It's equal to 1/2 sine of t plus theta, and then plus 1/2 sine of, well, theta minus t, right? Make that substitution. Bx is theta, minus ax is minus t. So we have this, right? So how can I get to like, sine t, sine theta? Well, how about this? Differentiate. with respect to t. Right? If I differentiate this equation with respect to t, I get minus sine t cosine theta. What's the derivative of this with respect to t? Well, it's cosine of t plus theta, and then the chain rule gives me, to quote my 4-year-old, nothing. Nothing. I didn't do anything. It's like, what did you do, Benjamin? Nothing. I did nothing. It usually means he did something. Cosine of theta minus t, but this time, the chain rule on the inside function gives me a minus 1. Because I'm differentiating with respect to t. So all of that in mind, what does this give us? This gives us that, oh man, son of a gun. Look at this. Sine, it should still be sine. Sorry about that. Anyway, so the point is, the identity here is sine t, sine theta is 1/2 cosine of theta minus t minus 1/2 cosine of, well, we could say theta plus t. I mean, whatever order you want to write them in. There's the identity for sine sine. Let's see here. As a quick check on my answer, what happens if I put t equal to theta? I'll keep the theta. I would get sine squared theta is what, 1/2? What happens when we put t equal to theta? Well, cosine of 0 is 1, right? And over here, I get minus cosine 2 theta. Now, I happen to know that that's the identity for sine squared from my previous work, so that gives me confidence that I haven't made a sign error here. So anyway, we're collecting identities at the moment. You realize we could also write, I mean, I've written the identity in terms of multiples of x, right? But it's useful to also have the identity written in terms of just like plain variables like cosine, this one, cosine of t, sine of theta is 1/2 sine of t plus theta plus 1/2 sine of, theta minus t. By the way, sometimes you'll see this identity written as 1/2 sine of t plus theta minus 1/2 sine of theta minus t, t minus theta rather, because sine is odd, right? So you can always pull minuses out. So as you're, checking your formula versus my notes or something, beware of this issue. Okay. So there's a lot of trigonometric identities that you may not actually be aware of yet, right? Like I think most people know sine squared plus cosine squared is 1. You know the identity for secant squared. You may or may not be aware of the adding angles formulas for sine and cosine, right? But, okay. So now that we have all this, let me work an example. So if I wanted to integrate, let's say, sine of 2x times the sine of 11x, how would I do it? Which identity do I want to use to make quick work of this guy? So sine, right? So it's the integral of 1/2 what? I think I need to use here, think of t as being 2x and theta being 11x. So I've got 1/2 of cosine. So theta minus t is 9x, yeah? And theta plus t is 13, right? Now, how do we integrate stuff like this? We break it into two pieces, right? The one is the cosine of 9x dx. The other is 1/2 cosine of 13x dx. I need to make a u substitution for these, right? So for this one, I'll say u1 equals to 9x. So du1 is equal to 9 dx, right? So dx is 1/9 du1. For this one, I'll make a u2 equals to 13x, which gives me du2 is 13 dx, or dx is 1/13 du2. So with those u substitutions in mind, that gets me to the integral, let's see here, 1/18 integral of the cosine of u1 du1 plus 1/26 integral of the cosine of u2 du2, right? What's the integral of cosine? Sine. Very good. And so what we got here is 1/18 sine of u1 plus 1/26 cosine. Oh, excuse me, good grief. Cosine must be sine of u2. Don't forget to add a constant at the end. And then, of course, we go back to x's. So we got 1/18 sine of 9x plus 1/26 sine of 13x plus a constant. Now, my question for you guys is it really necessary to write all of this out? I mean, it kind of depends on where you are. When I'm teaching Calculus 2, I don't write this down. When I'm teaching Calculus 2, and I face an integral of a function that I know, that's elementary, like cosine, and all that's been done is that the argument has been multiplied by a number, I just divide by that number for my antiderivative. In other words, when I'm teaching Calculus 2, I go straight from this point here to this point here. This is my Calc 2. Calc 2 default. Yep. I mean, that's all that happened. And, you know, if you guys want to learn that and do that in here, that's fine. If you want to show your work, that's fine. If in the problem on the test I say, you know, make your u substitutions explicit, then you need to write down the u that you did, you know? Another example of this, let me just do a couple, sort of lightning round. If I have integral of e to the 2t dt, if I have the integral of 2 to the 3t dt, if I have the integral of the hyperbolic cosh of 3x dx. So I just go, aha, 1/2 e to the 2t plus a constant. I do 1/3, 1 over the natural log of 2, 2 to the t plus a constant. 1/3 sinh of 3x plus a constant. I mean, it's totally reasonable that you get to the point where you can see those things without actually going through the mechanics of the u equals 2t, u equals 3t, or u equals 3x substitution that got you that 1/2, 1/3, and 1/3 there. Okay. Let me next turn our focus to some trigonometric integrals, which are less about your mastery of this example here is it's almost 90% trigonometry and 10% calculus. I mean, this is you're just completely stuck unless you have a deep understanding of trig identities, right? It's just that. The next bunch of examples I'm going to show you, they're really either about the Pythagorean identity for sine and cosine, the Pythagorean identity for secant and tangent, or repeated application of the double angle formulas. Here's one of the double angle formulas. The other double angle formula, we'll put it up here. Cosine squared theta is what? Same, but what? 1 plus cosine 2 theta. I think I worked that out last time. I derived it from the secret trig, right? So let's talk about integrals of powers of sine and cosine. Let's start with that. Power 1. We already know how to do that, right? Integral of sine is minus cosine. Integral of cosine is sine, right? So fine. I don't even write those down. How about integral of sine squared theta? What's that? It's integral of 1/2, 1 minus cosine 2 theta, right? And if I adopt my calculus 2 mentality of skipping over a little bit of detail here, the 1/2 pulls out. Integral of 1 is theta. Integral of cosine 2 theta is minus 1 over 2 sine 2 theta plus a constant. There you go. The half is from a u equals 2 theta substitution, which I did not write down. How about the integral of cosine squared? Oh, and my bad, like this right here, this is not allowed. We don't just write integral cosine squared, we write integral sine squared d theta. The d theta is not an optional notation. It has to be there, okay? My bad. Integral of cosine squared theta d theta, it's the same but with a plus instead of a minus. So it's 1/2 of theta plus 1/2 sine 2 theta plus a constant. All right, now for the first, I would say, interesting, less trigonometric, more based on u substitution kind of idea. N equals to 3. So this was n equals to 2. Now let's look at cubes. What if we were integrating sine cubed theta, d theta? How's this go? Well, think of it this way. This is the integral of sine squared theta times sine theta d theta. Does this give you any ideas? If I want to make sine theta d theta my du, what's that make u equal to? So let me say that again. If this is du, or perhaps minus du, what should I make u equal to? How about cosine theta, right? If u is cosine theta, then du is minus sine theta d theta. So this could be minus du if I make that substitution. But if I make that substitution, what about the sine squared? How do I change a sine squared to u? Because u is cosine. So how should I change sine squared to cosine? What do we know? We know cosine squared theta plus sine squared theta equals to 1, right? So I can trade sine squared for, well, 1 minus cosine squared, right? Which is 1 minus u squared in this context. If u equals cosine, then sine squared is 1 minus cosine squared, which is 1 minus u squared. And so what I'm facing here then is the integral of u squared minus 1, distributing the minus through, du. Can we do that integral? Like, yes, all day long, right? This does not require great mental energy. The integral of u squared is 1/3 u cubed, right? Integral of minus 1 is just minus u plus a constant, and then we go back to cosine. So the answer is 1 cube, listen to me, 1/3, 1 cube, what's wrong with me? 1/3, well, that's a new misspeaking. 1/3 cosine cubed minus cosine theta plus a constant, right? Now, I don't know, like, this is one of those examples I like to just take a step back and go, whoa. Because if I just wanted to guess like a function that when you differentiate it, it gives you back sine cubed, I don't think in 1,000 years I would just straight guess 1/3 cosine cubed minus cosine theta plus a constant. Like it is not at all obvious that the derivative of this is that. And yet that's what this work indicates. Now that I've done sine cubed, can you do cosine cubed? If I can do sine cubed, can you do cosine cubed? Integral of cosine cubed theta d theta, that's the integral of cosine squared theta cosine theta d theta, right? So let cosine theta d theta be my du. In other words, I'm going to let u equal to sine. So if u is equal to sine, that makes this 1 minus u squared, and we're left with the integral of 1 minus u squared du, which gives us u minus 1/3 u cubed plus a constant, which gives us sine theta minus 1/3 sine cubed theta plus a constant. There you go. That's the integral of cosine cubed. So actually, integrals of odd powers of sine or cosine are pretty easy once you have this in mind. What if I asked you to integrate like the 5th power of sine? What would that look like? See, that's the integral of sine squared of x squared, right? Times sine of x dx. So what should you do?